Welcome back for part 2. As promised in part 1, we will look at significance testing for mu1 minus mu2. So this should be pretty predictable right now. We're going to have our null hypothesis be mu1 minus mu2 equals something. And what we're going to be dealing with is the fact that there is no difference between the two means. In other words, mu1 minus mu2 equals 0, or the null hypothesis is that mu1 equals mu2. And the alternative hypothesis is going to be one of three things. The difference is greater than 0, less than 0, or not equal to 0. And if our three conditions are met, we can proceed with calculations. So, to do a test, we standardize x bar 1 minus x bar 2, and we can calculate a sample t-statistic, a two-sample t-statistic. To find the p-value, we will use the t-distribution with degrees of freedom given by our technology, and we're going to use the technology today, or using the conservative approach of picking the smaller of the degrees of freedom from our two samples. And again, if these conditions are met, we can proceed doing these calculations. Random. The data must be produced by a random sample of size n1 from population 1 and n2 from population 2, or by two groups in a randomized experiment. Normal. Both population distributions are normal. That's good. Or if both sample groups are large, that is, the central limit theorem is applying to both of our sample groups. Independence. Both samples or groups themselves and the individual observations in each group are independent. When sampling without replacement, we check that the two populations are at least 10 times as large as the corresponding samples. So again, two things built in here. The samples themselves must be independent of each other, and the individual observations must be independent. So here's our picture summarizing all of this. If our conditions are met, our null hypothesis is mu1 minus mu2 equals the value. Compute the test statistic using this formula. And we find the p-value by calculating the probability of getting a t-statistic this large or larger in the direction specified by the alternative hypothesis, HA. And guys, remember, this is something that's asked all the time. Interpret the p-value. The interpretation is that it's the probability of getting a value, a t-statistic, this large or larger in whatever direction our alternative hypothesis is specifying. And again, we're using the t-distribution, degrees of freedom, either technology or the conservative method by picking the smaller of these two degrees of freedom from our samples. So, I'm going to run through this without the calculator first, then take a jump to the calculator and run through that way. So we are looking at, does increasing the amount of calcium in our diet reduce blood pressure? And the relationship that examiners have found is that the relationship is strongest for black men. So we are going to do a study that looks at, does it make a difference or not? So we have 21 healthy black men. They volunteered to take part in the experiment. They were randomly assigned to two groups. 10 get a calcium supplement. The control group of 11 receive a placebo that looks just like the identical. The experiment was double-blind. Remember, that means the participants don't know, and neither do the experimenters. The response variable is the decrease in systolic blood pressure for a subject after 12 weeks. An increase appears as a negative response. So if their blood pressure went up, it's going to be a negative number. So negative numbers are bad here. We want the blood pressure to go down. So here is a dot plot of our data. Here's our data itself right here. 10 in group 1, 11 in group 2. We want to perform the significance test where the null hypothesis is mu1 minus mu2 equals 0. And the alternative that mu1 minus mu2 is greater than 0. We're trying to look at, does this pill help? So we want our alternative hypothesis to be in the positive direction, which would be the direction for decreased blood pressure. And we define our two parameters, and we state alpha being 0.05. Our conditions, random. 21 subjects were randomly assigned. Normal. With such small sample sizes, we need to examine the data to see if it's reasonable to believe that the actual distributions are normal. So here are box plots, and here are normal probability plots for these data. The box plot shows no clear evidence of skewness and definitely no outliers. The normal probability plot in the placebo's group looks very linear. The normal probability plot of the calcium groups shows some slight curvature. With no outliers and no clear skewness, the T procedures should be pretty accurate. And due to the random assignment, these two groups of men can be viewed as independent. Individual observations should be independent also. Knowing one person's change in blood pressure gives us no information about another. So we don't even need to worry about the 10% condition here. It's not applicable. So let's go. We've got our conditions. We are going to perform our two-sample t-test for the difference. We calculate our t-score. We're going to use 9 degrees of freedom. We picked the smaller one. This sample has 10 degrees of freedom. This one has 9. So we use our table, and what we find at 9 degrees of freedom and an upper tail probability, or with a t-score of 1.604, well, 1.604 isn't here. So the best we can do from this table is to say that, well, the probability, this upper tail probability, is going to be somewhere between 0.5 and 0.10. We don't know exactly what it is because we don't know exactly where in between them our t-score falls. And therein is the problem with not using technology. Technology will get us a much more accurate value of the p-value. However, because the p-value is definitely greater than 0.05, our alpha, we found that it's between 0.05 and 10. We failed to reject the null hypothesis. The experiment provides some evidence that calcium reduces blood pressure, but the evidence is not convincing enough to conclude that calcium reduces blood pressure more than a placebo. So let's jump to our calculator, and we're going to do the same test. So into a data and statistic page, we are going to put our data, calcium, placebo. We go to our calculator page, go to menu, statistics, stat tests. We're going to do two-sample t-test. And our data input method is going to be data. Our list 1, calcium. List 2, placebo. Alternative hypothesis. We had mu1 minus mu2 greater than 0. So our alternative hypothesis will be mu1 is greater than mu2. And we are never going to use pooled data with means. That is only for proportions. So never change this when we're dealing with means. We hit OK. Notice here our degrees of freedom that the calculator was able to use, 15.59. Our p-value was approximately 0.064, much more precise. We have our x-bar, our standard deviations, n1, n2, but the important thing is this p-value, and that is greater than our significance level. We are rejecting the null hypothesis, or we are failing to reject the null hypothesis. I'm sorry. Anywho, back to this.
It's 8 o'clock.
We can estimate the difference in the true mean decrease for calcium and placebo using a two-sample t interval for this. To get results that are consistent with a one-tailed test at alpha equals 0.05, we use a 90% confidence interval. Remember, the confidence interval is the middle part, and it always has two tails. So alpha 0.05, we use a 90% confidence interval. The conditions are the same ones as we used when we did our t-test. So we are just going to move into the calculation. And we could use the calculator again, but if we use the degrees of freedom of 9, the critical value is 1.833. Our confidence interval would be negative 0.754 to 11.3. So we're 90% confidence that this interval captures the difference in true mean blood pressure reduction on calcium over placebo. Because the 90% confidence interval includes 0 as a plausible value for the difference, we cannot reject the null hypothesis against the two-sided alternative at the 0.1 significance level or against the one-sided alternative at the 0.05 significance level. Whew! Okay, so let's talk about how we need to be careful using our two-sample t procedures. Two-sample procedures ideally come from samples that are the same size and similar shapes. And when that's the case, the probability values from our t-table are quite accurate for a broad range of distributions, even when sample sizes are as small as 5. And we've seen this before for our normal condition. If the sample size is less than 15, we can use a two-sample t procedure if the data in both samples groups appear close to normal. That is roughly symmetric, single peak, no outliers. If the data are clearly skewed or if outliers are present, do not use t. So it has to look like it's normal. Our samples must be that way. If our sample size is at least 15 but less than 30, our two-sample t procedures can be used except in the presence of outliers or strong skewness. So this gives us some flexibility for things less than 30. And for large samples, for 30 or more, we can always use our t procedures. That is what the central limit theorem tells us. Some cautions and considerations to make. In planning a two-sample study, you should choose equal sample sizes. It gives you better things to compare. We never use pooled two-sample t procedures. Never, never, never pool. This is only for proportions. We're safe using two-sample t procedures for comparing two means in a randomized experiment. But we don't use two-sample t procedures on paired data. And you shouldn't make inferences in the absence of randomization. The results may not be generalized to the larger population of interest. And this is something that probably a lot of statistical studies make an error on. The samples weren't truly random, and so they can't truly be generalized to the population on the whole. So here is our summary. It should look very similar to what we've been doing for the last several sections. And that, ladies and gentlemen, is all for Chapter 10.